hello, I will just record on my own end here, and some of those videos will come up later since we are in the middle of post-processing. My recordings here, the Big Blue Button recordings, also need to post-process. So just to give it some time, and you'll find them either here or on YouTube. The links should all be on the school webpage. Here, for example, and in the respective tutorials of my fellow speakers, you will find the further links as always. So about the title, this is my third and last session here in this Hausdorff School, and I was going into some theory about the encoding and ordering conventions of elements in p4est. I will continue a little bit to wrap it up today, and then I'll go into some of the important algorithms. The first one that is natural after discussing the ordering of quadrants is the partition. And then there is refinement and coarsening. We had some questions today on how you could transfer data between the old and the new mesh after refinement and coarsening. So I'll give some examples there. And then there are a couple more interface functions that just briefly were mentioned today. The iterator to enumerate all the neighbor connections in a local part of the mesh, to be able to set up any kind of degrees of freedom globally consistent in parallel, and to exchange any kind of information across faces, edges, and corners. And then there's a general search function. You may be wondering, if this is a tree-based software, then there should be searches if we want to just go to find anything, elements, other elements, points. If you do particles, for example, Toby had this example on the gyrokinetic solve in this plasma with all these charged particles, and if you have a non-uniform concentration of particles, you may want to go find them efficiently and see which of the particles I'm interested in are on which process, things like that. So there's a search function that is very general, and I'll try to cover that too. So where were we yesterday? We were looking at linear indexing in the sense that all leaves of the tree have an ordering sequence. So for each leaf you can tell if it's less or greater than any other leaf in terms of some given ordering scheme. So I don't want to read all this here, and this is part of some lecture material I had, but let me point to some of those things here. So we had expressed or encoded a quadrant by the coordinate of its lower left corner, which is a tuple over the dimensions. So we have a certain number of integer bits for the first coordinate, second, and so on until the last. So in 3D we would have a free tuple of integers. And we have a priori fixed the maximum level that we allow, just for convenience to know how long our coordinates will be, because they are bit strings. They're regular integers that have a certain number of bits, and we need big L bits for each coordinate to go down in refinement from the root big L times to the smallest possible leaf. And each of these refinement levels increases the number of bits by 1 per dimension that we need to encode the location. So how could we try to find this equivalence of the x coordinates with the space filling curve idea? Suppose we just define a function called linear ID, and we would begin with the root. The root, what is the root? It is an element that has x, y, and z coordinates 0. The lower left corner is the origin, and it has level 0, right? So constructing the root is trivial, just setting x and L to 0. And then we say, okay, we just have one element anyway in this mesh then, or in this tree, so this is all per tree. So the linearity is naturally 0. Then if we refine, we go to 8 times as many elements in 3D, or 2 to the power of dimension many elements. So instead of 1 element, we have that many more. So which of all these elements we look at is just depending on which child we're considering. So all of the refined elements have a unique child number between 0 and 2 to the power of level and 2 to the power of dimension minus 1. In 3D it would be 8. We have 8 possible children. So for each of these children we can encode or compute the linear ID as a function of the child number and the parent. So if we go from some x and L element, and then we take a child number j here, so j is between 0 and 2 to the power of d exclusive, then we parameterize this function with the appropriate level, so the child has increased level by 1 here. Then we just define this inductively by the linear ID of the previously known element, the parent, which we scale up by 2 to the power of d. In binary, this means that we left shift by d bits. Right? And this frees up d more bits that are now necessarily 0, that come in from the right, and there we will just put down the child number, which also has d bits at most, or exactly, right? So we left shift by d bits and populate the new least significant bits with the child number. And we can do this, this is an inductive definition, we can do this as deep as you want. And naturally you will get a number that is in exactly the correct range between 0 and 2 to the power of a little d, little l for a certain level. Right? So for each level you'll have in 3 dimensions 8 times bigger range of quadrants. So this is, you can look at this as a construction of a uniform mesh, but of course each element of an adaptive mesh is part of a, say, virtual uniform mesh at that level, and within that mesh it has this number. So basically if you go adaptive, you will be mixing elements of different levels. You will have different linear IDs that correspond to different levels, so we would have to make sure that we compare them in the same frame, right? So how could you make this unique in the sense that you always express the linear ID for any element, no matter how big it is, as the linear ID of its lower left corner at the finest possible level, big L, right? So that's what you could do, and then just define the overall linear ID of an element as the linear ID of its deepest corner descendant at the maximum level. So another way of looking at this is that an equivalent expression of the quadrant x and L is a sequence of refinements from the root. And we have exactly little l many refinements beginning with the root, and each refinement requires a parameter, the child ID, which is a d-bit number. Right? So we have each of these calls parameterized by 3 bits that I will just call j0, j big L minus 0 to j big L minus 1. Big L minus level, right? So you see that the sequence between these numbers is little l many. Since each refinement path is unique, these numbers are unique. And these numbers are nothing else but the child IDs that are used on the previous page to construct the linear ID. There are a couple more equivalences. If you want to read up in detail, I'd suggest the YouTube videos on my recent lecture that are still being post-processed. So I think 4 of them are online. The other 3 or 4 will be coming up shortly, and I will be going through these pages here. So there are a couple of corollaries, but the main thing to remember is that there is a one-to-one correspondence between the quadrant as an element of some uniform mesh at some level and the linear ID that counts to the cells in this uniform mesh. There's actually, this is the converse formula, right? If I had this recursive definition of linear ID going down, you can of course go back up by right shifting by d bits and then taking the original linear ID. The parent will have a linear ID independent of which child you are using to get to it. So this right shift is rounding down, and the child ID that was identifying the input argument is no longer relevant. So this is another expression. The linear ID is nothing else but the bit concatenation of the various child numbers used to get to it from the root. And if we want to go down to level big L, we would just fill up with zeros until we have little d times big L many bits. we could store all our quadrants as linear ID. We could, if we wanted to, it would be equivalent to storing x, y, z. And but right now we're thinking x and L was not such a bad choice, since most algorithms are really very fast in the x and L representation. We have some experiments coming up comparing the two, but that will have to wait. So within this linear ID, you can define a successor, a predecessor of an element. That would be the same size element coming right before or after in this curve. And this is easily expressed in terms of a successor and a predecessor function that would just take the inverse of this linear ID, do +1, and go back, right? Very simple. That's of course not how we do it ideally in the previous version, or in the current released version of the code. This is actually how we construct a tree. So let me show you this real quick here. So if we go to the new function, which is here, and again, if this font is too small, you may try to full screen your big blue button presentation window. There's a button that looks like 4 white arrows on the top right. At some point we will really just create all our local elements. There are different ways of doing that, but what it comes down to is a very simple loop that I'm trying to find. Here. So we have a certain number of local quadrants, and the quadrant partition is disjoint. If we call a new function, there is the option that I would recommend is to use the fill uniform option. So you would get actually uniform mesh at a certain level that is partitioned in parallel by the input communicator. And what we do in this, this is really old code. This is from 2007 or so, some of it. We actually go to the quadrants index, the local index, and then we just call the inverse linear ID function by counting through the sequence, and for each sequence inverting the linear ID to get the x and L, which is exactly what this function does. It would be faster to replace this with successor calls, which is actually work that we have in the upcoming branch that we're merging soon. So this is again a dimension-independent way of working with the elements in the trees, right? So none of this depends on the dimension, except for how many children do you have per refinement. This is 2 to the power of d. You can illustrate the equivalence between the coordinates and the linear ID some more. If you do all of this in binary, then that's easy to see. So here, for example, I would have my favorite picture of a 3-level down refinement. So the coordinates go from 0 to 8 in each dimension. This is a 2D example, and this element here that I shaded has a lower left corner that is at x equals 3 and y equals 5, right? So you can write down those 3 numbers. Each must be between 0 and 7 inclusive. If we go 3 levels down, and then you can write each of this as binary. 3 would be 0, 1, 1, and 5 would be 1, 0, 1. And then we flip all these bits around, so we construct the child ID of the first refinement from the root to the first level 1 element. So this is the root here. And to get to this quadrant, we need to take child ID number 2, which is the top left. And the top left means in x direction we're taking variant 0. Variant 1 would be the right side, variant 0 is the left side. In y, we're taking variant 1 because variant 0 would be down and variant 1 is up. So we have a 0, we have the child ID is 1, 0 binary, which is 2, 0, 1, 2. And this 2 is nothing else than the combination of the first y bit 1 and the combination of the first x bit 0, which will be here, right? So this child number J2 is the child number of the first refinement, which takes 1 bit from each coordinate. And then we do this as explained earlier, and we're using all the bits of the coordinates and arranging them alternatingly by dimension, and then we get this number, which is 39, and that's exactly, if you count in a uniform measure where we are, the sequence number of this element. Right? So why is this so important? This is important because we can partition there very quickly and fairly. Partitioning means having the union of elements over all processes, and we want to split them by process and assign a disjoint partition. Partition is, as a word, by definition, disjoint, right? So we would just separate the elements by process and put a certain stretch of the sequence range to some process. So we partition by going through the range of quadrants and chopping it up and assigning the quadrants in order of the processes. So this is what I was wanting to say about partition. So now Donna mentioned 17 processes. I think I like to use really strange and odd numbers. How would you partition 64 elements, as in this 2D example, between 17 processes? Well, there's a formula that is not my idea. It was used before. One person who worked with it was Tiankai Tu, back in 2000, even before 2007. So we indebted to him for a whole bunch of insight. He came a little bit before our time, was doing his PhD at CMU. So if we have big N here as a number of quadrants, say 64, we have big P processes, say 17. Then we can compute offsets by going to the process numbers, little p, that is between 0 and big P inclusive if you want, and you can just evaluate this formula for every p, and you will get numbers between 0 and 64 in order of little p, which means these O's are offsets that each process gets to point to the first quadrant that is going to that process. So the offset is the beginning sequence number of quadrants for a certain process. So that means each process gets as many elements as there are in this range, and the range is the offset of the next guy minus the offset of this guy. And this is how to compute the partition of 64 elements between 17 processes. You could actually partition 4 elements between 17 processes, then some of these ranges would just be 0, right? Some processes will be empty. It is important to make sure that your code survives if there are 0 elements per process on some process, because that is the case that occurs, period, right? So you don't want to crash on 0 quadrant processes. We don't crash, it is perfectly possible. So one version of this tree construction, if you begin with a uniform level little l, execute this on some little process little p out of 0 to big P exclusive, you would basically just have this very simple loop. Allocate space for the known number of elements, which is in my code this array of quadrants, and this array will encompass x, y, z, and the level in 3D. And then we just go through these guys locally and construct them by the linear ID inverse function. Faster version is just constructing the first element on that process by linear ID inverse, and then filling the others by calling its successor function. That I didn't explain, but maybe that's an exercise. How would you create this successor function just using ancestor, child, parent, and some other building blocks? It's in the code. The solution is in the code if you want to look at this. So partitioning basically means for each process will have a different big E0, the first quadrant on that process. If a process is actually empty, we just say it has the same E0 than the next one that is eventually non-empty. Which means we could actually encode the whole partition in parallel if each process would share its position E0 with all others. So since E0 is just 16 bytes, if you don't account for metadata that we may want to add, and this is entirely practical, and that would be, if you know MPI, that's the MPI all-gather version. So that would give us an encoding of the whole partition boundary without knowing any quadrant information of remote processes. So this is a powerful feature of tree-based refinement. If we want to know which part of the domain belongs to which process, we can determine this just based on an array of E0s where each process contributes just one position. This is naturally by thinking of this as a top-down search algorithm that will zoom in and on the way figuring out if the zoom box is split in parallel or if it's just on one process. And if it's just on one process, we're done. Right? And otherwise, we refine and continue in the search. But this is basically explaining the search function, which I wanted to go to later. So there's a picture. There's a picture here of a uniform mesh that I created with this prescription. I am choosing 64 elements in 2D 3 processes. You get your offsets by the formula, you get your numbers by the formula, and you see this partition is fair. It is element counts plus -1, so partitioning is always perfectly fair if you want it to be. And you see that process 1 gets 2 different areas here, this one on the lower right and this one on the top left. And the zigzag line here is nothing else but the representation of the sequence, how the sequence number is equivalent to positions and how these positions align by sequence. So that means we are able to create an initial mesh by just creating the local elements in some uniform mesh. I'm getting a question about partitioning. I will get to that pretty soon. So, but how do we get from a uniform mesh to a more exciting mesh? We would refine and coarsen. But that is actually really easy since all the quadrants are stored as a linear array in sequence of this linear ID. We can run a loop, and whenever we get the information from our application that this quadrant really should be replaced by children, then we would basically take out that one and replace it with the children in the sequence of their children order. So that means if a certain quadrant comes after all the ones before in the sequence and before all the next ones, if I replace it with the children, these will also, by construction, in sequence, be after all the ones before and before all the ones after. So refining and coarsening are invariant in terms of this order. That means we do not need to reorder anything on refinement and partition. We do not need to sort, right? So just we basically, most of p4est is writing loops over this linear array of local quadrants, and there is no sorting except for rather involved algorithms that we sometimes need, such as balance, right? But most of what we do here can be done without sorting, because the sorted property is an invariant that is preserved by linear traversals, and we don't need to resort. And it is as easy as that with refine and coarsen. Let me go through the code here. Of course, the code got a little more involved since we allow both recursive and non-recursive refinement and so on. Let me try to narrow this down. So this is, we express this as this loop really as a while loop, since the number of elements grows in refinement, right? So we don't know in advance how many elements we will eventually get unless we pre-analyze the array of markers for refinement, which we don't really want to do, or the application maybe can do that for us if they really want to, and they could tweak this algorithm. But we go through these quadrants, and whenever we refine, we replace this one quadrant with its children, and if we go recursive, we just continue there until eventually we're done with all the descendants and go to the next one. And if we refine, we would actually create 8 children out of this one parent, which needs to be done somewhere. Here. So we really create the children and eventually throw away the parent. And that's a 3D and that's a 2D function. You see again, we have dimension independent code. Mostly just by coupled if-defs you can compile the 2D and the 3D code from the same text here. The question, of course, that came up earlier is how would we transfer data? So there are 2 ways of storing data with p4est. One is using this pre-allocated fixed size per quadrant that you can do. And the other way is knowing the local number of quadrants from the p4est data structure or from L nodes, for example, where it is present. And then you would allocate this data yourself in application space. So this refinement function is suitable to transfer data that is in the quadrant. So this is the first case. And how is this done? This is done by calling a callback function each time we replace a parent with their children. So we call this function here, replace function. So there's a callback that gets passed the parent and the children, and from those you can access the pre-allocated user data in all of those, and you can do the interpolation that you want independent of us. So right, p4est is completely data agnostic. And here, where is this called? There's the replace function, right? So this is where we call the replace function just after creating the children and before throwing away the parent. That's actually an addition by Toby. In the past, the replace function was not originally a feature that we had, but it is convenient for this case. So you could possibly use this to interpolate application data, but that is difficult because in the middle of this refine function, you will not even have created the allocation, since you do not know until this function is done how many elements we will get. So if you're choosing the other approach, data is in application space, then you would, after refinement, allocate however many elements are in this new mesh, and you still have the data from the old mesh, right? So you have the linear array, and accordingly, in your application space, sequenced in the same way all your numerical data from the old mesh, and then you have all the numerical data for a new mesh, but it's not there. All you have done is allocated the space for it, and now you need to compute it. So how do we get this data from the old structure to the new? And that is a way that we have done way back in pretty much all of our codes. A very nice example is in the Mangle code, that is Lucas's discontinuous Galerkin elasticity code. And the way he does this, or yes, say it's a field project. So this function takes data on an old mesh and a new mesh, and the mesh is both refined and coarsened. So we have an original mesh, and then we call refine, and then we call coarsen, and then we have the target. And now what we can use is the fact that the sequence between parents and children is invariant, right? So all these elements that are not changed between those two meshes will be in the same relative order as before, or in the same relative order, in the sense that we do not, refinement coarsening does not permute. So that means we can have 2 pointers, one pointing into this old data, one pointing into the new data, and we iterate both pointers in sync. And if both elements are the same size, that means there was no refinement or coarsening. We will just copy the data from the old to the new location. If we had a refinement, we will have 8 target data blocks for one source data block, and then whatever the application wants to do, it can do to interpolate this data. So the pointer would then be advanced for all the children in the target and just by one in the source. And if we actually coarsened, we would do it the other way. We have 8 elements that we process in the source and 1 element in the target, but all of this is in sequence. Right? So you can have 2 pointers, and Lucas calls them, I think, PK and LK here, or PK and CK. Let's see. So those are the pointers. One is into the source mesh, the other one is into the refined and coarsened mesh. And those are the bounds. We grab the level actually of those cells, and then we see if we will just see if there was if the previous mesh cell was bigger, that it means there was a coarsening that you see here. So we will do some numerical stuff to process data and store it in a new location. If there was a refinement, that means the new level is bigger than the old level, then we basically do something else numerically, a projection. Well, we would project on coarsening and interpolate on refinement, right? And the third case is when there was no refinement. So in this case, we will just copy things. Right? In Forest Claw, we do it even a little better than that. Since the data for each patch is allocated per patch, we would just hook the pointer from the old to the new mesh and otherwise not do anything. So this is how we can refine and coarsen in application data space, which is what we do in Forest Claw, and what can you do? You can do without the replace callback. Right? The question applies for partitioning. So if we partition, first of all, how does partitioning work at all? So we're done with refinement and coarsening very quickly here. Partitioning is nothing else than, what does it do? We have the same global number of elements. So the big N sub big P is the same before and after. What changes is the offsets. So if we're coming into partitioning, the offsets of the source mesh will not be all that nicely equipartitioned, right? But we can compute the offsets of the new mesh by that formula. And then we have the old offsets here that are not in any nice kind of intervals usually, and we have the new one, which is the target partitioning that we like. Usually it's a uniformly or equipartition, right? And that means we have two arrays of the same length. Basically, both of these offset arrays are views onto the same set of elements. Just the location by process is different, which means we can see how the offsets are different between the source and the target configuration, and wherever there's a difference, that means we need to send this message. So you can encode this very, very simply here, just having the old O and the new O prime here. So each process, little p, will very easily compute the set of sender processes and a set of receiver processes by just doing figuring out this comparison condition wherever the windows match, right? And we do that in partition, and partitioning is nice enough to ship the inside allocation, the quadrant user data for you. So if you call partition and have pre-allocated user data, then it will be there after partitioning without you doing anything. If now you chose to have your data in application space, then you have this data and you can allocate, well, you would have to, the data is different from the p4est data structure, right? So you would have this old data, the old p4est. You can make a copy of this old p4est and partition the copy. That's at least how we did this always so far. And then the target partition will tell you a changed local number of elements. The global number of elements stays the same, but the local number of elements changes on partition. And then we have this, and this is enough to allocate data for the new partitioned mesh. And then we have the old and the new p4est data structure, and we have the source data and the target data. And then there's a function that you can call to do the messaging that will just populate your target data with the partitioned data. This is written up in this relatively recent preprint. That's the 2018 preprint that's coming up in tomes soon. So that's linked on the webpage as citation 1D in p4est, and you can read on the little helper function for repartitioning. I should put this on here. Wait. Right. So again, sorry for missing out here real quick. This is the 1D preprint. That is also linked on the webpage, and this is the paragraph on repartitioning. So there are functions in the code. You can just search for p4est transfer, and they can do both same size data per quadrant or even HP simulations where you have variable size data. Right. Unfortunately, the Mangle code is something you would have to ask Lucas for. I'm sure he will be happy to give it to you, but please email Lucas tomorrow or ask him. There is a question to partitioning here. I think I will not go in detail over those algorithms. They will do nothing else than working with these formulas that I have here. All right, so if you feel free to look through the code of p4est transfer. It's quite instructive, and see what it does. So I've used a lot of time on partition, refinement, and coarsening, but of course those are very important top-level algorithms that everybody will need to run. And if you have any reasonable amount of data per quadrant, I really suggest to do application space data. But now you know how you can refine and coarsen this, and how you can transfer this after partitioning. So this should get you going to have a simulation that is evolving over time or in any other way. So what is missing still is how you would inform your numerical code on parallel neighbors, I would think, right? So we do have the ghost layer structure in p4est. That is actually, I would recommend, if you want to learn more about that, to go through the according tutorial. So in the school webpage, we can go to the ghost tutorial here. And this will have you construct the ghost layer in the draw. It will also show you some functions that, again, can be used to ghost exchange application space data, which is what we are calling in forest law on the patch data Donna is allocating. So check this out. This is a function that you can use to create to get ghost Halo application data to the local process, and then you can search for your elements in the ghost layer. Again, the ghost elements have an ordering, and the ghosts are nothing else than a linear array of ghost quadrant coordinates and level pairs, like in my lecture, in sequence. Right? So it is you can binary search them very efficiently, even though there are still slightly more wholesome ways to go through the neighbor connections, right? So with ghost layer is what we did back in the day. It's sufficient to search it and to connect communication patterns if you don't want to use our ghost exchange but write it yourself, for example. The more evolved way of dealing with neighbors is calling p4est iterate. So the first question is, why is this thing called iterate? Well, it's not the worst name for what it does. Let's look at it here. I got a question here. Could you comment on how much would work or break for Hilbert space fill-in curves in place of Z curves? In terms of partitioning, nothing would break. In terms of refinement and coarsening, nothing would break. In terms of really, it would go through. What we would have to add though is writing the relation between sequence index and coordinate will be different. So that is the only thing that changes from our ordering to Hilbert, which actually means that the little functions that create a parent, a child, are different from what we have now. So you would have to implement the small functions that all these three-liners that do parents, descendants, ancestors, child IDs, and so on for Hilbert. But you could use the same high-level general algorithms. If you want to do that, actually, my former grad student Johannes Holke has written a code that is general with respect to space-filling curves and element shapes. So he did tetrahedral space-filling curves, and we have prisms and triangles, and I worked on pyramids. So that is an infrastructure that can easily accommodate Hilbert curve. You would just have to write all these low-level element functions. You can check out the code. It's called TED code. But again, the high-level functions will not change at all. Just the low-level functions that have a relation to the sequence formula will be different. So there's another question on longest edge, propagation path, instead of red-green refinement. I'm not sure how that applies to squares and cubes, honestly. So I'm not sure how to answer this right now. Let's go through Iterate. Yes, it's for simplicities, so that relates to TED code. But there we need a recursive refinement, just as in p4est. So that means we do not use some of those classical longest edge things that you would use otherwise. So can you see this? The iterate function, basically what it does, it's a top-down traversal of the mesh internally that works with the local quadrants and the ghost layer. So it is parametrized with the local forest and the ghost quadrants that were assembled. It does not know about any data in application space, right? This is really just to encode neighbor relations. What it does, it will zoom into the whole mesh recursively, and it will pass each element exactly once. And for each element, you will get a callback on the volume, and then it will also find each phase between two elements exactly once. So for each interface between phases, you will get a callback that will tell you if it's for each. So it will be called from two with two quadrants as parameters. One will be on the left side of the phase, the other one on the right. And if it's adaptive, maybe on one side there are four squares and 4 cubes, and on the other side there's one. And it will be called exactly once for this interface, and it will there's an edge callback and a corner callback that work the same way. So there's some encoding convention about the data that each of these callbacks will return to you. So the volume callback is the simplest one. It will just be called once for each local element. The phase callback will be called for each locally relevant phase connection. So even if at least one of the elements on both sides of the phase is a local element, you will get a call of this phase quadrant. And phases are easy in the sense, since there's always a left and a right. But what about edges? If you have an edge, you can have multiple quadrants rotated around it. So if you look at it like this, it could be a star of some sort. So corners, this is a 2D, so edges are not in this one. So corners and edges are more complicated. But nevertheless, this is all very well documented here. So please go through the comment blocks if you like to. And iterate, basically, you see it is parameterized by the ghost layer p4est. You can pass some data to callbacks just to keep context. So this is not the p4est user data. This is just for you to use. And then you just provide the callbacks, and this thing will just run efficiently top down through the mesh and give you a call for each topological interface. So it may appear reasonable by now that this is the function that Toby used to construct the L nodes structure. So this comes before L nodes, since we could also use this directly to set up some kind of topological representation of the whole mesh. So if you have a code, say you do, Tommy mentioned the Rabiat-Tomar code, if you do phase connections and volumes, and you want to figure out the communication pattern of fluxes, then you could call this function with a volume and a phase callback. And in the phase callback, you will get for each remote element also which process that is, and they will all be called in a defined sequence. So after this function is done, you will know for each process how many phase neighbors there are, so you can allocate the buffers for MPI messaging. You can copy your data into them and then communicate this, and also the receivers will know about the sender, since this is all symmetric, right, between sender and receiver. So of course, for each local element that has a remote neighbor, you would allocate receive buffer space and do your messaging. So this is a universal function that can be used to implement pretty much any interface to numerical codes. If it's a node-based code, if it's a flux-based code, if it's anything else, if you want to construct a full topology of everything, you can use this. Of course, it may be easier to just use p4est if you want to access it via DM, right? So these things are all interesting for people who want to write their own interface to a numerical library or a numerical application code, or those who want to figure out how does forest law exactly work with p4est, how does p4est work with p4est. But it's also really cool to put together a self-contained simulation that is just a couple hundred lines of code. So we have an example that uses Iterate. Toby wrote that. That's a very simple finite volume code that uses Iterate for phase connections. It's under steps. So these steps are actually, for our standards, reasonably well documented programs. So that's not it. It's number 3, I think. Yeah, so that's a simple advection solver that uses Iterate to figure out communication and flux transfer. Let me look through the questions real quick. Oh, it's Lucas actually works on TED Code. He's a student of mine and Johannes Holke. So if you have questions on triangles and tetrahedra, please make an appointment with Lucas in the break room, or just email if you want to. So this is Iterate. With Iterate and all the other functions earlier, partition, refine, coarsen, new, and ghost, that's everything you would need to inform some numerical code about the mesh and efficiently transfer and interpolate data. What may be a functionality that you need on top is to search things. So say you do a particle method and you want to have a large CFL, so the particle would move outside of the ghost layer in one step, right? You say you have a whole bunch of sensors. Donna is running some simulations of sea level and waves, and of course in tsunamis, and of course there we have gauges, and these gauges are known locations we need for each process to find which gauges are within its range or its partition, right? And then even if we know this, we need to know for each gauge which is the element that contains it. So we have a whole bunch of completely general objects that we want to search in the mesh by some geometric criteria, and we have a functionality that is well documented that is called just that, p4est search. Here, let me go through the interface again. So I really suggest to read through the documentation. This one is pretty good. Not those little helper functions, but the big ones here. So this is search local. Suppose for these gauges, those are inputs or output to the simulation, and it's sufficient if the local process finds the subset of object that is in its partition, then it will write a file, and every other process will write another file, and in the union you will have all the data. So here you will just say, I have so and so many points, and a point can be anything. It doesn't need to be a point. It can be an object. If you want to do collision detection, have a bunch of bricks that falls down the roof and piles up. You want to know how they intersect with meshes and coordinates and so on. Each point will be your representation of such a brick, for example, right? And its position. And then this function will just call a callback function that you will basically, for each it will give you pairs of a point and one search zoom quadrant, right? So it begins with the roots, which does not need to be an actual quadrant. The quadrants are usually much finer, but the binary search goes with big search quadrants, smaller search quadrants, and so on. And for each step, it will ask you about one quadrant that it uses for search, and of course this quadrant is a position by its coordinate x, and level you will be able to know its exact location, and geometry, since the geometry is stored on your side, and a point, and this point is some convention that you basically define, right? And then you can return 0 or 1 in terms of this point fits into this quadrant or not, and then we will just scratch it or not and run through the whole recursion. And when this function is done, you will have associated all your points with elements. You can associate a point with no element or with more than one element, all by just using the callback function correctly. So this is great for outputs of sensors, receivers, sources that are somehow strangely geometrically located. You can, and that's a recent addition that's also in this 2018 Thomas paper that's coming up. Hopefully for 2020, but that's citation 1D. You can actually also search the partition. If you remember this big E0 element, each process communicates the location of its first quadrant, and this is mathematically sufficient to encode each and every boundary between processes, right? Without knowing any other elements, we know the shape of the partition just by this minimal data that we share, which means we can actually locate points in remote process partitions. So this is the version of the code here where you would call it pretty much the same way, and it will give you search quadrants that may overlap remote processes, but still it's about, does a certain point match a certain quadrant, and you will return yes or no on that question. And in the end, you will get a positive result for a local point. So you will basically learn, hey, this is on the local partition, or you will get the exact process number of a point, and then you know that is the process you need to send a message to ask about this point. So this function will identify remote process locations for any points that you're looking for. I have used this just for demo particle simulation, for example, here. Right? So this is a particle tracking simulation, which is completely parallel adaptive. And I was using the search functionality to find if a particle leaves the process and goes to a different process, I need to know which process did it move to. And this is the function I was using. And it works great. So I'm suggesting, if you're into computational geometry or particles or any other of Lagrangian schemes, and check out this function. So this is really what I wanted to say today about high-level algorithms. With those that are covered, you can actually write a numerical application without using any other libraries. Of course, the question if this is smart or not, if you wouldn't rather use PETC or would use Forest Law or DEAL2, is something you may decide. But I'm sure there are developers out there, and I'm sure there are people who want to use p4est to interface into an existing code, right? So the Wyoming people have a bunch of existing codes, and they really want to use p4est as a mesh information provider, and those functions are exactly that, what they will need to interface the two. So if you have some kind of code that is hexahedral based, adaptive or not, parallel or not, you can likely just chop off its low-level mesh representation, replace it with p4est, and no user will ever know the difference, right? So this works surprisingly well, and those are the functions. I will stop here for my third lecture here on AMR. Any questions that I should answer right now? I'm watching the chat here, so I'm recording this video on my end, and I will read out the questions here. So it's about explaining the phase transform and the connectivity. Sadly, no. Those videos are basically on theory. They're not on p4est. They are on concepts on how would you write a child, a parent, a linear ID function. So the specifics of p4est are still best experienced with the code. So I would really say try out the tutorial on connectivity and just work through some of these exercises, look at the code, and this is great, just grabbing a piece of paper, figuring out the face number and the number of the neighbor face, the edge number, and how many trees are around this edge and how are they flipped and all that. So this is something that's really that can just be done learning by doing here. So please check out the tutorials on connectivity there. I know it's not exactly easy, but we hope that it is well defined in terms of what's in there. So this is the documentation of the 3D connectivity that tells us how tree roots are connected. And this numbering convention here, or the ordering convention, especially orientation, this will show up everywhere. So in the iterator, if you have a phase connection, then if this connection is rotated or flipped in some way, is encoded with the exact conventions that are documented in this connectivity file here, right? So this is p8 connectivity, and there is really no way around going through this convention and reading a bit of the code there, and again working through this connectivity tutorial will help quite a lot. Future directions of p4est. So the current version 2, what we call it, it's if you want to download the cleanest version, it's pre-v3 develop. So let me type this. This has the least amount of dependencies and old stuff that we didn't need anymore. And this interface will be stable forever. You can use with these functions. There's really nothing else you would really need. I didn't actually mention the 2-to-1 balance function, right? So you can do a 2-to-1 balance refinement to smooth out your mesh and to make sure that each element neighbor is at most a factor of 2 size different. But we are doing something new, of course. So together with my students Michael and Tim, who are also here, we're working on a version of p4est that comes, say, separately from the current p4est. So the current p4est will stay up functional. We'll actually optimize it a little bit. Tim is working on optimizations to have maximum level 29 available in 3 dimensions for very deep refinement, optimizing partition, and a couple other things. But we're actually looking into a new interface that is reduced and will just go through Iterate and nothing else. It will support multi-threading, OpenMP, and maybe some device offloading. We'll see about that. But it's supposed to be OpenMP plus MPI, so for people who want to work on shared memory nodes and have some idea of the OpenMP partitioning, that's the main thing that we're adding, right? So any more questions? If not, I will thank you all for the attention today, this afternoon, and we'll be looking forward very excitedly to a couple more lectures by everybody else but me tomorrow and Friday. So please be in touch. There are exercises. Just go to work. There's tons of material that will keep you busy if you want to. And I'll be happy to come back to you with more answers later. Thanks.